Welcome. In this video, we will move from FDTs to GFDTs, grouped frequency distribution tables, and we'll discuss how to read them, show how they are built, and how to interpret and glean information from them. We will introduce the key vocabulary terms used with GFDTs and by extension with their graphical representations, histograms. And we will explore the nature of discrete data briefly, with careful attention to how it can help us better understand our data. In particular, we will focus on the differences between discrete and continuous data. Let's look at the difference between an FDT and a GFDT. Recall, FDT stands for Frequency Distribution Table. A GFDT is a grouped frequency distribution table. As the name suggests, we will group some of the frequencies together. But first, we need to see why this is necessary. Here we have the exam scores from a class of 25 students. As indicated, there were two versions of the exam, but for now, we will focus on the entire set of values as a single data set. For this data set, we see that the minimum is 58 and the maximum is 100. And if we were to build an FDT for this data, we would need a table starting at 58, 59, 60, 61, all the way up to 100. For all the values from 58 to 100, that would be a total of 43 rows. Remember, the purpose of an FDT is to summarize the data in a format that takes up less space, but in this case, we only have 25 data values, and it is unclear how a table with 43 rows would provide a more concise summary of the data. Simply put, a table with 43 rows would take up far more space than actually listing out the 25 values. The FDT would defeat the purpose of a summary to take up less space. So let's build a GFDT. To do this, we will use the back-to-back stem and leaf plot for this data set. Again, we are treating the data values as one data set, but this stem and leaf plot provides a conveniently organized version of the data to allow us to count how many data values are in given intervals in the range of the data. What we will do is use the implied grouping structure from the stem and leaf plot. Namely, we are going to count how many data values are in the 50s, the 60s, the 70s, etc. We will record the frequencies in this column. First, we see there was only one value in the 50s, as highlighted here, both in the raw data and in the stem and leaf plot. We see that there were 4 values in the 60s, again, clearly highlighted here. There were also 4 values in the 70s, a total of 9 values in the 80s, 6 values in the 90s, and only 1 value in the interval 100 to 109. And this now has accounted for all the students' exam data. For the FDT, we need to clearly indicate the range of frequencies that have been grouped together, if you will. From the stem and leaf plot, we were grouping by the 50s, 60s, 70s, etc., and we can write this clearly in the first column of the table. And now we have a GFDT. Again, the idea is that we group the frequencies for 80, 81, 82 up through 89 into one group, the 80s, which we have labeled as 80 to 89. And there was a total of 9 exam scores that fell in this interval, as indicated by the frequency column. Unlike the FDT, which would have taken up 43 rows, the GFDT takes up only 6 rows. And this does achieve the purpose of summarizing the data and taking up less space. Let's look briefly at the GFDT for the students who took version A of the exam. This is a good time to comment about the convention for groups with 0 frequency. As before with FDTs, frequency polygons and stem and leaf plots, if you have a range of values with 0 frequency occurring in the middle of the data, this row should not be omitted from the table. And if we were to look at this GFDT, we see that there were no scores in the 70s. However, this does not mean that we would drop that row from the table. We include it and clearly indicate that there were no scores in that range with a frequency of 0. Now this table also has a 0 in the first row for the range 50 to 59. As there were no scores in the 50s for version A of the exam, and as this is at the extreme end of the table, it probably is best to not include that row in the table, unless there is some other story that this row helps tell. And in this case, since we might want to compare to the version B group, which did have a score in the 50s, one might argue that you could actually keep this row here. Let's return to the GFDT for the entire class of 25 students. One key thing to note is that if you are only given the GFDT and not the raw data, then you have a summary that takes up less space, but it comes at a cost. In particular, we actually lose information about the actual data if we only have the GFDT. Let's explore this idea a bit further with another example. Here's the GFDT for a small data set. This data are student scores from an Algebra 1 placement test given at the start of class. This pretest was used to help make sure students were placed in the correct class. If they scored too low, they could be moved into a pre-algebra class, and if they score too high, they could be moved up into an Algebra 2 class. The placement test consisted of 20 questions, and the frequency for each range of values is reported in the GFDT. Just as a quick aside, convince yourself that there were 38 students who took this placement test. To demonstrate how we have quote-unquote lost information about our data with this GFDT, let's think about how many students in our data scored 6 on the pretest. Well, in truth, it would be impossible to say how many students got a 6 just from the info presented in this GFDT. In fact, the only thing we can say is that there were 5 students who had scores in the range of 6 to 8. Now, it could be that all 5 in this group scored a 6. But it could be that the lowest score was actually a 7 or an 8, and in either case, there would be 0 students that scored a 6. So we can't say how many students scored a 6 on the pretest, but we do know that the frequency of 6s is between 0 and 5. Note, this is an example of how the story helps us decide whether or not to include a 0 frequency row at the far end of a GFDT. In this case, the last row indicates the maximum of the placement test. And the 0 frequency simply indicates that none of the students did indeed score the maximum, or any value from 18 to 20 for that matter, which might be interpreted as none of the students were underplaced into too low of a class, as a high score means they might need to be in Algebra 2 instead. Okay, let's introduce some of the key vocabulary terms associated with GFDTs. These terms are also used with histograms and grouped frequency polygons, which are the graphical representations of GFDTs. For our purposes, we will omit the last row that had a 0 frequency, and we will demonstrate the vocabulary terms using this smaller GFDT for the same data. The lower class limits are the smallest value that appears in each group. In this case, the groups of scores have been labeled as lower number to higher number. It is this lower number for each class that is the lower class limit for that class. These values have been highlighted here in orange. The number line at the bottom of the screen will help us visualize the groupings and the vocabulary terms. Next, we have the upper class limits. These are the largest values that appear in each class. Note, the term class or bin is used interchangeably for any given group of values. For example, the second class has a lower class limit of 9 and an upper class limit of 11. For this interval of values, there were 13 values in the data set that appeared in this range from 9 to 11. The upper class limits have been indicated here in teal. The middle of the class is called the class midpoint. There is a more archaic term you might encounter called the class mark, but this term seems to have fallen out of fashion and generally is only used with discrete data. Data like this, that has a fixed increment between possible consecutive values for the variable being measured, and we'll talk more on this shortly. However, in this case, we'll stick with the term class midpoints. In this case, we can just take the average of the class's lower and upper class limits, and this will give us the class midpoint. The class midpoints have been indicated here in green. Between each class, we can imagine a fence that separates one group of values from the next group of values. We will call these fences the class boundaries. The class boundaries are indicated here with the pink dashed lines. The value for a boundary can most directly be calculated by taking the average of one class's upper class limit and the next class's lower class limit. For example, the boundary between the third and fourth class would be the average of 14, the third class's upper class limit, and 15, the fourth class's lower class limit. This boundary is 14.5. Repeating this process, we also get the other class boundaries of 8.5 and 11.5. If we extend this pattern to either end of the table, we can get the boundaries on the outside of the table as well. The lower boundary would be at 5.5, and the uppermost boundary would be at 17.5. Again, we just continued the observed pattern in the class boundaries. But I will briefly note here that the discrete unit for this data is 1. The smallest each quiz score can change by is 1 point. And what we see here is that the distance between classes is 1 discrete unit. So the fences are halfway between, or half of a discrete unit above and below the class's upper and lower limits. Again, we will have more to say on the discrete unit shortly. Now let's introduce the most important term for GFDTs, the class width. The class width can be formally defined as the distance between any two consecutive class boundaries. As is indicated here, we see that the class width is 3, the distance between 8.5 and 11.5. And it is the same distance between any pair of class boundaries. In truth, the class width can be obtained using any consecutive pair of values from the classes. For example, the distance between two consecutive lower class limits will also give the class width of 3, or the distance between two consecutive upper class limits, or even the distance between two consecutive class midpoints. The key is that if you compare the corresponding value from any two consecutive classes, you should get the class width. This assumes the class width is consistent for the GFDT, and this is one of the rules associated with conventional GFDTs, and we will talk about this in a future video. Before we move on from this, there is one very common error that we will highlight here. The one thing you cannot do is subtract the lower class limit from the upper class limit to get the class width. For the second class, these values are 11 and 9, and if you subtract 11 and 9, you get 2. But 2 is not 3, and thus this approach does not give the class width. The reason this approach doesn't work is because it does not account for the discrete unit. Let's use an analogy to help understand why this approach is incorrect. If you have been given an assignment of reading pages 30 to 50 in one of your classes, we know that this means that we don't need to read 20 pages, but going on the idea that we need to read everything on all of the pages listed, this means we need to read all 21 pages from 30 to 50. It is the same idea here. When counting the number of the possible values for a variable in a group, we need to count the total number of possible values, not just calculate the difference between the numbers, at least not the difference of the upper and lower class limits. Again, you get the class width from the distance between the corresponding value for any two consecutive classes. Let's explore this idea of the discrete unit a bit further. We will define the discrete unit for a variable as the smallest unit by which the values for the variable can increase or decrease. For our Algebra 1 placement test, there was a point for each correctly answered question, so the discrete unit was 1 point. US shoe sizes are a variable that has a discrete unit of 1/2. For example, you might wear a 9, a 9.5, but there is nothing between those two values of 9 and 9.5. The cost of an item in US dollars has a discrete unit of 1/100th, $0.01 or 1 cent. This is the smallest increment between two prices that you can observe. Let's say a psychology professor gave a final exam of 60 multiple choice questions where each question was worth 2 points. In this case, the variable is the exam score and the discrete unit is 2 points. Let's look at this example further, an example with a discrete unit of 2. Here is the GFDT for the psychology final exam we just mentioned. 60 questions, each worth 2 points. Thus, the discrete unit is 2. And the very nature of the way the numbers are reported in the scores column gives us a clue about this. Note that the smallest class ends at 48, meaning a score of 48 would be counted in this grouping. But the next class starts with 50. Again, a score of 50 would be counted in this second grouping. Wait, where does the score of 49 go? Well, as we know because of the context, it is not possible to have a score of 49 on this test. You get a 48 if you have 24 questions correct, and a 50 if you have 25 questions correct. There is no way to get 49. And that's because it's generally true that you can't get partial credit for multiple choice questions. So here are the lower class limits for each class, and here are the upper class limits for each class. To elaborate, for the highest class, this represents the group of scores from 110 to 120, a total of 6 possible scores: 110, 112, 114, 116, 118, and 120. From the GFDT, we see that there were 36 students who scored in this range on the final exam. Here are the class midpoints for each class. These are just the points that fall in the middle of the group. But in this case, notice that it is not possible to actually have a score that is a class midpoint, i.e., it is not possible to have a score of 115 or 91 or any of the other class midpoints, which are all odd numbers. And here are the class boundaries between each of our classes. And if we extend the pattern, we get the boundaries for the farthest most of the classes. Now, if we subtract any consecutive pair of values from either column, we find our class width of 12. And this is just the number of points in each class, 6, times the discrete unit, 2. And this is not a coincidence. One of the important things about building and interpreting a GFDT is to make sure the table correctly conveys the nature of the data to your reader. While it may not be wrong to report the table with a discrete unit of 1, it is more transparent if we build it in this fashion, in which we make it abundantly clear that the discrete unit is indeed the number 2. So we can now start to tease apart the differences between continuous and discrete data. For our purposes in this class, discrete data is data for a variable that can change by some smallest fixed amount. Or it is data that has been presented in a way that represents it as having some smallest fixed amount. Say annual salaries reported to the nearest $1,000. Mathematically speaking, there's a more formal way to define the distinction between discrete and continuous, but it doesn't really help us at this stage in our introduction to statistical thinking. So let's give a couple of analogies that help us see the difference between continuous and discrete data, and we'll see the discrete unit helps with this. Let's use the barnyard for our context. Chickens lay eggs, and this is an example of discrete data. We can have 2 eggs or 3 eggs, but if you have 2.25 eggs, well, then all you really have is just a mess. Of course, you can't have part of an egg, so the discrete unit here is 1. But for cows that give milk, this is an example of continuous data. Here a cow can give you 1 liter of milk, or 2 liters of milk, or any fractional portion in between, 1.2 liters, 1.25 liters, 1.2577632 liters, etc. With continuous data, there is no smallest discrete amount by which the value can change. Essentially, you can have just about any degree of precision, even if the data isn't actually recorded to that degree of precision. For example, a person's height is usually recorded to the nearest whole half inch or maybe even a quarter inch, but technically you could get a much more precise measurement if desired. And that's where we'll stop for now. Thanks for your attention. I hope this brief demonstration was useful to you.